In this video, I wanted to talk about the stress-strain relationship. So the main equation for this is that stress equals the Young's modulus times the strain. So this here is stress, which is just force over area. This here is the Young's modulus, also known as elasticity. And this here is the strain, which is the change in length over the original length. And this is true for either tensile or compressive loading, and it's only valid in the elastic zone. So if you start getting plastic deformation, this equation isn't going to hold anymore. Now, if we plug in this delta L over L and this F over A, I'm actually called F at P, and then we rearrange to solve for the delta L. We get this equation here, and I like to call this the play equation, just an easy acronym to remember it by. This is a very common equation that you might see on the PE, so it's good to just have that one memorized. Okay, so now I wanted to do an example problem. So a 1-inch diameter steel rod with a Young's modulus of 29,000 KSI with a relaxed length of 24 inches is loaded with a 1,000 pound tensile load. So we have a rod 24 inches long, it's loaded with a tensile load of 1,000 pounds. And we are asked to find the stress in the rod and then find the axial elongation. So to find the stress, we're just going to say that stress equals the force over the area. Our force here is 1,000 pounds. The area, this is a circular rod, we're given diameter, so the area is going to be pi times the radius squared. The radius is 1/2 inch. This is an important thing to watch out for. Make sure you're using the radius, not the diameter. Make sure you read the question carefully. So that comes to 1,273.24 psi. So that is our stress. Now to find the actual elongation, I'm going to use that play equation from before. So delta L equals PL over AE. I'm going to rewrite this P over A as stress. So the sigma stress times L over E equals 1,273.24 pounds per square inch times the original length of 24 inches divided by the Young's modulus, which is 29,000 times 10 to the 3 pounds per square inch. I wrote it like that so these would cancel here, and we're just left with inches. So our axial elongation, which is the change in length, is going to be .0.001 inches, about 1,000th of an inch. But yeah, this type of problem is pretty common from what I've seen on the PE practice exam. So this is a good one just to have it memorized how to solve these. But I hope that helps.